Alright, so for the second part of this homework, we are going to be revisiting another problem we face in MEB. And this problem is focused on a continuous stir tank reactor. And in this reactor, we have a first order reaction that we have reactant A going to reactant B. On the outside of the reactor, to keep our temperature at a steady state initially, we have a water jacket around it that has a constant flow of water to keep temperature at a set value. And with that water jacket, we are assuming that the flow rate of the water is going so fast that the temperature of the jacket stays consistent throughout. So I'll start by drawing this reactor out and driving some equations that we'll use to then simulate this reactor and look at the change in temperature of the reactor and the change in concentration over time. When we change the temperature of the coolant, we increase it to decrease the amount of heat transfer that occurs, and we'll look at what that does to the temperature and consequently the concentration. So I'll start on my iPad here, and I will derive these expressions that we will use. So I'll draw a scenario out to give us a better idea of what we're going to be looking at. So I draw the reactor, and in the reactor we have reactant A going to B. And that could be like an isomerization reaction that involves just one reactant changing into a different isomer of itself. So we have some feed going into the reactor, and we'll have some volumetric flow rate Q in, and then we have some initial concentration that we're feeding into the reactor, Ca in. To assume a steady state or a consistent liquid level, we're just going to be drawing off at the same point that we feed in. So we're not going to have any change in volume to make the problem simplified for us. So we'll draw the liquid level. So that will be Q out. And we're assuming that this is going to be a very well stirred tank, so the concentration will be consistent throughout the reactor. So Ca in the reactor here will be the same that goes out of the reactor, so that will also be Ca. And like I said, we have that water jacket going around the reactor, so we'll draw the water jacket in here. And we have some flow of water at a very high rate to avoid a temperature change throughout the jacket. And we'll say the temperature of the jacket is initially Tc naught. And we're going to be changing Tc naught to some value of Tc that we want to investigate. So in order to solve this, we both need to set up a material and energy balance for the CSTR. So we'll start with the material balance, and for that I'm going to use a mole balance as my starting point for a continuous stir tank reactor. So a mole balance for the reactor looks like the molar flow rate in, which I will derive in a second, minus the molar flow rate out, plus the reaction rate constant, not the reaction rate constant, just the rate law, times the volume. And since it's well stirred, you can assume the volume is spatially consistent, so you don't have to use anything special. We can just use this volume term here. And that will be equal to the accumulation, which is the change in moles over time. So let's kind of break this down into some variables that I just defined up top there. So FA0 is the molar flow rate in, so that will be equal to the volumetric flow rate times the concentration in. And like I said, Q in and Q out are the same because we are at a steady state. So Q in equals Q out. So minus the volumetric flow rate out will just be Q in again times Ca. Like I didn't label it as Ca out because the concentration in the tank is the same as Ca out. So we'll be using Ca on this side to describe the molar accumulation. So we'll leave that as Ca, so it'll be more useful to us. Plus Ra. So the rate law here, RA will be equal to negative, because we're consuming A in this reaction, negative K times the concentration of A. And we'll look at further into what K is in a second. So it'll be, instead of plus, it should have minus KCA. And that will be equal to the change in concentration, dCA, times volume over dt. And since volume is constant, you pull out of the derivative on this side. Oh, shoot, I forgot the V term here. KCA times volume equals, perfect. And like I said, K has a certain value here, so K will be equal to exponential of the activation energy over RT, I believe. We'll come back to that one, but I think that's what we will be using in our expression. So we can plug that value in separately. I think our problem has some different parameters that we're supposed to use, and we'll touch on that when we slide over to Python. But for the overall mass balance, we'll simplify this to make it a little bit cleaner and get things in terms of dCA dt. So we'll move this to dCA dt will be equal to Q in times the concentration in minus the concentration of the tank. That will be divided by the volume, and this will be minus, subtracted, this will be minus the rate constant times the concentration. The V term will cancel out there, so we don't have to worry about it. So there's a material balance for the tank, and that will allow us to look at the change in concentration over time, which will be nice because it will give us a good profile as the temperature changes. So for the energy balance, we'll do a similar thing. We'll look at the accumulation in the tank, which is the energy in minus the energy out plus the energy generated. And in this case, the energy in and the energy out, we want to relate the temperature of the fluid going into the system to the energy. And we're going to use the heat capacity to do so. So the heat capacity will just be C. It can be CP or CV in this situation because we have an incompressible fluid in water, or basically water, because we have a smaller concentration or reactant we're pumping into the system. So we'll just use a generic value as C for it. So C is the heat capacity, and that will be in units of joules per gram Kelvin. So in order to use this heat capacity, we need to cancel these units out to just get joules. So we're going to do so. The tank has a volume times the concentration in the tank times the density. So we'll get meters cubed times moles per meter cubed times gram per meter cubed. And we'll end up with that's what I wanted. We don't want the, sorry, we don't want the concentration in there. We just want the density times the volumetric flow rate, and that will be grams per meter cubed times meters cubed per second. So those will cancel out and give us grams per second. So we'll express the change in the energy in the tank as the differential of the temperature times the density of the fluid going into the system times the volumetric flow rate times the heat capacity C over dt. And we're going to move this over because we're going to need some more room. So just like the accumulation of energy in the tank, we'll use a similar relationship for the flow rates coming in to express the energy coming in. So we'll express that as the volumetric flow rate times the density. Oh shoot, this should not be volumetric flow rate, this should be volume, because that would still be grams. So the volumetric flow rate is just like the volume, but it's a units of time, which will help with this derivative here. So the volumetric flow rate times the density times the heat capacity, and then that will be multiplied by the temperature of the inlet. So Tn, so this is coming in at a given temperature, Tn. And that would still be what? Just make my units cancel out. Meters cubed times grams per meter cubed per second times joules per gram Kelvin. Cancel out, yes. So it'd be joules per second coming in, which is perfect for us. And then this will be subtracted by the molar flow rate out, which is still some Q. I think we used Q in earlier, so we'll keep using Q in, which is kind of confusing. So Q in times the density coming out times the heat capacity, and this time we're not using Tn, we'll use the temperature of the reactor here, because like I said, it's well mixed, it's well stirred, so it's going to be uniform throughout, sometimes C. And then subtracted from that, or I should say added, because we have an exothermic reaction occurring, so heat is being generated by this reaction. As the concentration of A is consumed, heat's being generated and added to the system. So usually we have the negative, sorry, not negative, but like we have negative the heat of the reaction, and in this case, since it's an exothermic reaction, the heat of the reaction is negative, so this will become positive heat of reaction. So the heat of reaction has units of joules per mole. So we want to have it in joules per second, so in order to do that, we're going to add plus the reaction rate, because the reaction rate will be in moles per second. So we'll say plus the rate constant K times the concentration of A times the volume, all over, or all multiplied by the heat of the reaction times the heat of the reaction. And then subtracted from this, we have this temperature, or this cooling jacket around the reactor. And with the cooling jacket, since it's a lower temperature, we're going to have some heat transfer out of the reactor. Heat will be lost to the jacket, and we can use an overall heat transfer coefficient, U, which has units of joules, well, in this case we'll say joules, joules per meter squared times Kelvin times seconds. So in order to cancel the units out, we'll subtract, so we're subtracting in this case, minus U, A, T minus the temperature of the coolant. Yep, that will work. Alright. So we can cancel some of these variables out to get a nice cleaner expression here. So it will be, since these are all constant, so it'd be, we pull T rho, no, we can't pull T out, sorry. We pull rho, V, and C out. And we'll have dT, d temperature over change in time, will be equal to electric flow rate N times rho times C times Tn. And these variables will all be the same, so we can just minus T, and then we'll have plus the reaction, the rate of the reaction times the enthalpy of the reaction, so plus K Ca V H reaction, and then at the end of this we'll have minus the heat transfer, minus AT minus TC. It's a little tight on the end there. So let's divide by some expression, or by some constants, and cancel things out. So we'll have dt over dt will be equal to, so these density, we're going to divide by each side by the density times the volume, which is going to be times the heat capacity. So these will all cancel out. We'll have rho, or we'll have Q over V Tn minus T plus KCA enthalpy of the reaction all over. Only thing that's canceling out is V, so I'll be over rho C, and then this will be minus UA T minus TC all over rho VC. So this will be our expression for the change in temperature in the reactor, and we look at based on the reaction rate that occurs. And then this is where's our mole balance. And here's our material balance. So with some defined parameters that we have given in a problem in a textbook, we'll then use these to actually simulate and use these expressions to look at how the temperature and concentration will change in the reactor as the time goes on. Alright, so now that we have those equations, we are going to use, I'll pull this up on my monitor here. You'll see on this computer monitor, you'll see the conditions that we're going to use to simulate how the concentration and temperature will change in our reactor when we change the temperature of the coolant water around the jacket there. So let's start cutting this out. So we're going to import numpy to np. We're going to import from scipy dot integrate. We're going to import solve underscore IVP. And then from plotly dot subplots, we're going to import underscore subplots. I can't turn time first. So these parameters that were given here, I'll define them and I'll talk about what they mean in terms of the equation we just defined. So while that's running, Q will be the flow rate going into the system. So like Q is the volumetric flow rate. It's going to be in liters per minute, and it's going to be 100 liters per minute. CAI, that's a concentration of the flow rate going into the system. So that 100 liters per minute has a concentration of 1 mole per liter. Tau I will just be the temperature of the inlet, and it's going to be 350 Kelvin, so the temperature of the stream going into the tank. V, that's just going to be the volume, and that's going to be 100 liters, the volume of the reactor. Rho, it's going to be the density of the fluid, which we assume to be mostly water, so it's going to be 1,000 grams per liter. C is the heat capacity that we want to use, and that's going to be 0.239. It's going to be in joules per gram Kelvin. V, okay, so they have the opposite, the negative value of the enthalpy of the reaction, so since it's negative already, it makes that a positive number, so we don't have to worry about subtracting a negative number to make it positive in our expression, so we'll say negative H reaction will be 5, and that's going to be 50,000 joules per mole. So ER, that is the parameter we're going to use to find the K value. The K value, I misdefined it in my expression. The rate constant will be equal to the K naught value that I'll define shortly after this, activation energy over the gas constant. So it'll be the rate constant times the exponential value of the rate constant, or the activation energy, the negative value of the activation energy over the rate, over the temperature, over the gas constant. So sorry, speaking that was not very clear, but I'll hopefully type that out and make more sense. So ER, so that's the activation energy over the gas constant, and that's going to be in Kelvin. K naught, like I said, will be the initial value that we use to solve for our rate constant, and that'll be equal to 7.2 to the 10th, that's going to be in minutes, negative first, so our reaction rate's based on minutes and not seconds there. UA is the heat transfer, overall heat transfer coefficient times the area, and we have a value of 50,000 joules per mole, or joules per minute Kelvin. TC naught will be the initial coolant temperature. So right now the problem has it defined as 300 Kelvin, so we'll stick with 300 Kelvin to start with, and then we'll change it. Ca naught is just the concentration, initial concentration of the reactor, and that will be 0.5 moles per liter. That will be an initial guess for one of our expressions that we define, and then T naught will be the initial temperature. That'll be another initial guess we'll use. 350 Kelvin here. Shift enter. Alright, so now we have all these variables defined. Let's go ahead and define our functions. So define right hand sides. The first thing we'll put in is the time, and the second will be the vector that we'll unpack. So for the vector, we'll unpack the temperature and the concentration, and that will be equal to the vector. So let's just, I'm going to write these expressions out to help me remember what we had. So we had d v d ca dt was equal to q. Since q in and q out were the same, it was d ca I minus ca, concentration of the reactor, concentration A minus concentration of the reactor. Minus, because we're consuming the reaction, K times Ca times volume. So it's the volume there. So like I said, K we didn't define properly. K will be equal to K naught times the e to the power of negative ER divided by T. So what it actually looks like is K equals K naught times E to the power of negative activation energy divided by RT. Since it's ER, it looks a little weird. So that's K, rate constant, is equal to the initial rate constant times the exponential value raised to the negative of the activation energy over the gas constant times the temperature. So that is what I was trying to say earlier. Just did a really poor job of doing so. Okay, so we have one of our expressions here, and kind of simplify it a little bit. Divide each side by the volume. So Q divided by V times the concentration difference of the inlet and the reactor. And since we have case or volume on both sides, we can cancel out that volume. So that's one of the expressions we'll be using. So we're going to return this value. KCA. Oh, and I should put this in lowercase. Oh, I don't want to. My bad, I don't need to run that. And then the next expression we're looking at, we are going to return. That was the heat capacity C times rho times the volume times the, wait, that was it, rho times times dt dt. Is there another variable I had to look at? Let's make sure my units cancel it up. So the density kilograms per cube. Out, so we have grams. That should be it. We'll see when we define the thing. So this was the accumulation of energy in the tank, and we relate the temperature to joules with the heat capacity here, and that was equal to the flow rate in, Q, times the density times the temperature difference between the two, times the heat capacity, sorry, and then times T, the temperature of the reactor, minus the temperature of the inlet, or actually Tn minus T, because Tn is the first variable there. So we have the flow rate times the density times the heat capacity times the temperature difference between the liquid going into the tank or into the reactor versus what's already in the temperature in the reactor. So T will be this variable. We're going to look at that, and we're going to turn and plot that one. This will be plus, since the reaction is exothermic, it's generating heat, and the heat will be added to the system, so it will be plus the negative enthalpy of the reaction. It's already negative, so it's positive now, times K times C A times the volume. So just like the reaction rate is based on a molar basis here, or not molar, a volumetric basis here, it's the same for the generation of heat on the enthalpy of the reaction, so we have to multiply that term by volume here, and then we're losing heat due to the temperature difference between the reactor jacket and our reactor itself, so we have some heat loss, which we'll define as UA times the temperature difference between the reactor and the coolant temperature. So UA is overall heat transfer coefficient times the area times that temperature difference. And both sides have some variables we can cancel out, so here we're just left with Q over V times, so the flow rate in over the volume of the reactor times the temperature difference of the fluid going into the reactor minus the temperature of the reactor itself, plus the enthalpy of the reaction times the rate constant K times the concentration, which those are all can stay, but this volumes cancel out, and we're going to then divide this expression for the enthalpy of the reaction divided by C times rho, and then this overall heat transfer coefficient times the temperature difference here. This will all be divided by C times rho times V. And include the variables from this side. So we'll have dt will be equal to the flow rate, volumetric flow rate into the system divided by the volume of the reactor times the difference in temperatures between the reactor stream, or the flow rate into the stream, flow rate of the fluid going into the reactor, subtracted by the reactor temperature itself, plus the enthalpy of the reaction, and the heat generated by the reaction divided by the heat capacity times the density, and then from that we subtract the heat loss, which is the overall heat transfer coefficient times the area times the temperature difference between the reactor and the coolant jacket, all divided by the heat capacity times the density times the volume of the reactor. So we'll clear this, and hopefully we didn't make any mistakes. So rho is undefined. That's why. Tn is undefined, and that's because we have it as tau I up top. Tc we have Tc not, so we'll keep it, well, change this to Tc. We're going to look at a different temperature shortly after. Okay, so it's solved, so let's go ahead and try to use solve IVP to solve this. We'll define some interval Tn to be, let's do 10 seconds. And we're going to need from that Tplot equal to np dot linspace 0 Tn, and we'll do 200 minutes. So solve underscore IVP. We'll have the right hand side function in there as our function. Tspan will be 0 t end. Our initial guesses will be CA0 and T0. This is capital. I don't want it to be capital. CA0, T0, and then the method will be equal to radout, and the dense output will be set to equal to true. So it looks like it's solved, so let's go ahead and take a look at it by plotting it. So we'll call this solution. So solve, well that's kind of weird. Let's call it results. Res.sol at tplot, and we want CA temperature. So I don't want that to actually, I want to say CA plot, and tplot will equal res.sol. Perfect. So let's take a look at it. Fig equals make underscore subplots, rows equal 1, columns equals 2. Fig dot add underscore scatter, x will be equal to tplot, y will be equal to CA plot, name plot CA, scatter will be the same thing. X will be equal to the temperature, or not the temperature, the time plot values that we just determined. Y will be equal to the temperature values, and the name will be equal to temperature. And fig. So this will be initially when our coolant temperature is 300 degrees. We'll take a look at what happens here. Oh, we have to put this in this different columns. Row equal 1, column equal 1, row equal 1, 2. So something's wrong already. Let's take a look at what I did. Let's see, let's put these in. Okay, so that's a lot better. So initially we have we expect it to be in the steady state, but these values here aren't exactly at steady state. So even with the values that were given, there might be some fluctuation, something that interrupts the steady state of our reactor, and that's where we get this variation here in the reactor. So if we wanted to, we can kind of dig deeper and find the root of the functions to find the values that would give us the steady states. But for now, that our case, we're not going to dig too deep in that. But what we're looking at here, so this is at when the coolant temperature is 300 degrees, the concentration eventually reaches a steady state, or something that looks like a steady state, and the temperature also will flatten out and reach a steady state over time. But we want to look what happens when we boost up this coolant temperature to 305 degrees. So there, when we increase the temperature to 305 degrees Kelvin, we have the concentration on the left and the temperature on the right. So what happens here is when the temperature of the reactor, temperature of the coolant is increased, there is less heat transfer that occurs as a result of the temperature difference between the reactor and the coolant. So with that change in temperature, the temperature of the reactor, or with the change in the amount of heat loss that occurs, the temperature will increase as less heat is lost to the coolant jacket. As the temperature of the reactor increases, the reaction rate will consequently increase as the temperature decreases. So as the reaction rate increases, the concentration here will decrease, and as the concentration decreases, the reaction rate will also decrease, and that will create an absence of exothermic heat released by the reaction. So that's why the temperature begins to come back down here. The temperature comes back down. Once the temperature comes back down, there is a higher, a lower reaction rate, so the concentration in the tank begins to accumulate because we have some value coming in, about 1 mole per liter. So the concentration begins to accumulate again. Once the concentration accumulates, the reaction rate will begin to increase again, and as the reaction rate increases again, the temperature will increase as more heat is released. So at 300 degrees, what happens? So we're initially at some given concentration. We begin to feed in more, or not more, but we're at some given temperature. Eventually, what happens here? I can describe this. So I guess as the temperature decreases here, the reaction rate will decrease, and we're inputting the concentration of A into the system with the flow rate coming in, and it's accumulating faster than it's reacted out until eventually reaches a steady state. So if you extend the Tn to, let's say, 100 seconds, yeah, it just flattens out as a constant value here when the reaction rate and the consumption of the concentration of A is equal to the amount of A coming into the system. But in the case of the higher temperature of the cooling jacket, you'll see it will continue to oscillate as that temperature increases and that reaction rate increases, and goes back and forth between temperature increase and reaction rate increase and concentration decrease and reaction rate decrease. So that kind of oscillates back and forth as time goes on.